Imagine standing in Alexandria in 62 AD. You're watching a hollow bronze sphere spinning furiously above a boiling cauldron, jets of steam hissing from bent tubes as it rotates faster and faster. You've just witnessed the world's first steam engine. 17 centuries before the Industrial Revolution changed everything. But here's the twist. The Romans saw this marvel, shrugged, and used it as a party trick. Today, we're uncovering why one of history's most profound inventions was forgotten for over 1,500 years, and what it teaches us about innovation, timing, and the strange path of human progress. The year is 62 AD, and Alexandria is the Silicon Valley of the ancient world. This Egyptian city, now under Roman control, houses the great library of Alexandria and the Museion, essentially an ancient university campus where the brightest minds of the Mediterranean world gathered to teach, research, and innovate. Walking these streets is a man known simply as Mechanikos, the Machine Man. His real name is Hero of Alexandria, though some sources call him Hieron. He's a Greek-Egyptian mathematician, engineer, and inventor whose resume reads like science fiction: automated temple doors, coin-operated holy water dispensers, wing-powered organs, and mechanical puppet theaters that perform entire plays without human intervention. But Hero's most extraordinary creation sits described on page 50 of his treatise Pneumatica, a collection of 78 different devices and inventions. It's called the Aeolipile, which literally translates to the ball of Aeolus, named after the Greek god of wind. Hero wasn't trying to solve an engineering problem in the way we think of it today. The Roman Empire was at its peak, stretching 2.2 million square miles across Europe, North Africa, and the Middle East. Competition among religious temples was fierce mystery cults. Traditional Roman gods, Greek deities, and Egyptian worship all vied for followers. Temple priests needed spectacle. They needed miracles. And that's where Hero came in. His job was to engineer divine phenomena: singing birds that appeared to breathe life, bursts of flame from seemingly nowhere, statues that moved on their own, and doors that opened by themselves when fires were lit on altars. The Aeolipile was born from this world of engineered wonder, not from a need for practical labor or transportation. And that single fact would determine its entire historical trajectory. The Romans had already mastered hydraulic engineering. Aqueducts carried millions of gallons of water across vast distances with precision gradients. They had water-powered mills for grinding grain. They understood principles of mechanics well enough to build the Pantheon's massive unreinforced concrete dome, which still stands today after nearly 2,000 years. Recent research from MIT has revealed that Roman concrete actually had self-healing capabilities thanks to lime-clasts mineral deposits that would react with water seeping through cracks, essentially repairing the structure from within. This isn't primitive technology. This is sophisticated materials science. So the question isn't whether ancient engineers were capable enough to understand steam power. The question is, why didn't they pursue it? How the Aeolipile actually works. Let me walk you through Hero's original instructions, which are remarkably precise. Picture this device. You start with a large bronze cauldron filled with water, positioned over a fire. From the lid of this cauldron rises a bent tube like a straw bent at angles that feeds into a hollow bronze sphere. This sphere is mounted on pivots so it can rotate freely. Now here's the clever part. The sphere itself has two L-shaped tubes emerging from opposite sides of its equator. These tubes are bent at right angles, pointing in opposite directions. Imagine them like the bent arms of a lawn sprinkler. When you light the fire beneath the cauldron, the water boils and produces steam. This pressurized steam travels up through the bent tube and into the hollow sphere. The steam builds up inside until it has nowhere to go but out through those two bent nozzles. As the steam jets out of these nozzles, Newton's third law of motion kicks in. Every action has an equal and opposite reaction. The steam shooting in one direction pushes the sphere in the opposite direction. Because the two jets point in opposite directions, they create a rotational force, or torque, causing the entire sphere to spin rapidly on its pivots. Modern reconstructions have shown the Aeolipile can spin at speeds up to 1,500 revolutions per minute with just 1.8 pounds per square inch of pressure. That's remarkably fast for such a simple device. What Hero created was actually a reaction turbine, the world's first recorded steam engine. It operates on the same principle as a rocket, thrust generated by expelling mass in one direction. The steam acts as the propellant, and the sphere as the vehicle being propelled. Hero's contemporary, Vitruvius, mentioned Aeolipiles in his architectural treatise, De Architectura, written around 3020 BC, describing them as brazen vessels that demonstrate the causes and effects of the great operations of the heavens and the winds. But it was Hero who provided the detailed construction manual that has survived to this day. Here's where the story gets interesting. We honestly don't know for certain what the Aeolipile was used for in ancient times. Hero's description simply explains how to build one and notes that the ball shall revolve, but he doesn't specify a practical application. Historical evidence suggests several possibilities. Temple wonders. Most scholars believe the Aeolipile was used to create religious spectacle. One variant involved hiding a boiler inside a hollow statue of a deity. Steam would exit through the nose or mouth, creating the impression of a breathing, God-inspiring awe and devotion among worshippers. Educational demonstrations. Vitruvius suggested these devices were used to demonstrate natural principles essentially, scientific demonstrations of air pressure, steam properties, and mechanical motion. Pure entertainment. Some sources describe it as nothing more than a sophisticated toy or party trick ancient equivalent of a desktop novelty that spins when you turn it on. What happened next is perhaps the most puzzling part of this story. The Aeolipile was documented, understood, and occasionally replicated for entertainment purposes. But for approximately 1,500 years, nobody seriously considered using it for practical work. During Europe's medieval period, Hero's works were largely forgotten in the West. However, the knowledge wasn't entirely lost. Byzantine engineers continued using similar steam-powered devices. The doors of the Hagia Sophia Cathedral, built in the 6th century, reportedly used Aeolipile-like mechanisms for automated opening. The Renaissance brought Hero's work back to Europe. In 1543, a Spanish naval captain named Blasco de Garay allegedly demonstrated a device to Holy Roman Emperor Charles V that could propel ships without wind, possibly combining Aeolipile principles with paddle wheel technology. Spanish authorities denied the claim, but it shows people were beginning to think about practical applications. By 1547, the first Italian translations of Pneumatica appeared. In 1577, Ottoman engineer Takal Din independently described a similar device. Throughout the late 1500s and 1600s, Hero's treatise spread across Europe, planting seeds that would eventually sprout into the Industrial Revolution. This is the question that haunts historians and engineers alike. Why didn't the Aeolipile spark an industrial revolution in ancient times? The answers reveal profound truths about how technological innovation actually happens. The efficiency problem. Modern analysis shows the Aeolipile produces negligible torque compared to later steam engines. A slave stoking the fire to run an Aeolipile-powered device would be far more productive just doing the work directly. The device consumes significant fuel, requires constant water supply, and delivers minimal useful work output. To put this in perspective, early industrial steam engines like James Watt has had torque outputs approximately 250,000 times greater than in the Aeolipile. The bore diameter alone was 2,500 times larger. These aren't marginal improvements. These are fundamental differences in capability. Metallurgical limitations. Efficient steam engines require the ability to contain and utilize high-pressure steam safely. The bronze and iron metallurgy available to Romans simply couldn't produce the precision components, high-pressure boilers, and safety mechanisms needed for practical steam engines. Even early Industrial Revolution steam engines were prone to catastrophic explosions, and they were made from superior steel. The economics of slavery. Perhaps most significantly, the Roman Empire's economy was built on slave labor. Why develop expensive, complex machines to replace human workers when slaves were abundant and cheap? There was no economic pressure driving innovation toward labor-saving technology. When slavery declined in later periods, Europe turned to water wheels and windmills technologies that were more practical given medieval metallurgy and manufacturing capabilities. It wasn't until coal mining created a desperate need for water pumps in deep mines that steam engines became economically necessary. It wasn't steam engine time. This concept, borrowed from science fiction, suggests that technologies emerge when all the necessary prerequisites align, not just technical knowledge, but social, economic, and industrial infrastructure. The Aeolipile appeared in a world that wasn't ready for it. The Aeolipile teaches us something crucial about technological progress. Having an idea first doesn't mean you benefit from it. Innovation requires technical capability, the metallurgy, manufacturing precision, and engineering knowledge to build reliable systems. Economic motivation, a problem expensive enough that complex solutions become worthwhile. Social conditions, a society structured to adopt and scale new technologies. Infrastructure, supporting industries and knowledge bases to maintain and improve the technology. The Romans had the first ingredient, but lacked the others. It's why the same invention, rediscovered 1,700 years later in a completely different context, changed the world. Despite never powering Roman industry, the Aeolipile wasn't useless. It preserved crucial knowledge about steam's potential for generating motion. When Renaissance engineers rediscovered Hero's work, they had a foundation to build upon. More importantly, it demonstrated that human ingenuity regularly outpaces human society. The gap between what's technically possible and what's practically useful can span centuries. The Aeolipile was a time capsule of possibility, waiting for the world to catch up. Fast forward to 1884. British engineer Sir Charles Parsons builds the first modern steam turbine generating just 7.5 kilowatts to light an exhibition in Newcastle, England. His design operates on the same basic principle as Hero Aeolipile. Steam expelled through nozzles creates rotational force. But Parsons had something Hero didn't: precision metallurgy, high-pressure boilers, and the mathematics of thermodynamic efficiency developed by scientists like Sadi Carnot. Today, steam turbines generate approximately 80% of all electricity in the world. Let that sink in. That ancient party trick from among Alexandria now powers modern civilization. Modern steam turbines are vastly more sophisticated than Aeolipiles, but the core physics remain unchanged. High-pressure superheated steam often, at temperatures exceeding 600 degrees Celsius and pressures of 280 atmospheres enters multi-stage turbines. These turbines contain dozens of precisely engineered blade sets. Each stage extracts energy while gradually reducing steam pressure, preventing excessive stress on any single component. The largest turbines can generate over 1,500 megawatts, enough to power 1.5 million homes. They operate at speeds around 3,000 to 3,600 RPM, directly coupled to electrical generators, producing alternating current at exactly 50 or 60 hertz, depending on regional standards. Modern control systems regulate steam flow, temperature, and pressure with extraordinary precision, achieving thermal efficiencies approaching 45% in the most advanced facilities. Power generation. Nuclear power plants use steam turbines driven by heat from nuclear reactions. Coal, natural gas, and even concentrated solar thermal plants all rely on steam turbines to convert heat into electricity. Combined cycle plants. Modern facilities pair gas turbines with steam turbines in combined cycle configurations, capturing waste heat from gas turbine exhaust to generate additional electricity. This increases overall efficiency from about 40% to 60%, a massive improvement in fuel efficiency and carbon emissions reduction. Marine propulsion. Large ships, including some modern naval vessels and cargo carriers, use steam turbines for propulsion. Nuclear submarines can operate submerged for months thanks to reactor-heated steam turbines requiring no atmospheric oxygen. Industrial applications. Petrochemical plants, refineries, and manufacturing facilities use steam turbines to drive heavy machinery while simultaneously generating electricity and process heat. Today, you can buy miniature Aeolipile kits as educational demonstrations. These copper replicas, operated by alcohol burners, spin dramatically while teaching fundamental principles of thermodynamics, Newton's laws, and mechanical engineering. They're used in physics classrooms worldwide, connecting modern students directly to Hero's ancient ingenuity. The Aeolipile represents one of history's most fascinating what-ifs. A device created for theatrical wonder, contained within it the seeds of the Industrial Revolution seeds that would lie dormant for 17 centuries before, transforming human civilization. Hero of Alexandria wasn't trying to change the world. He was trying to impress temple visitors. Yet his hollow spinning sphere demonstrated principles that would eventually power cities, drive ships across oceans, and generate the electricity behind the screen you're watching right now. The lesson isn't that the Romans were short-sighted or that progress is inevitable. It's that innovation is deeply contextual. The most brilliant idea at the wrong time is just a curiosity. But preserve that idea, record it carefully, and wait for the world to change, and suddenly that ancient party trick becomes the foundation of modern power generation. Next time you turn on a light, remember, you're benefiting from knowledge first documented in Alexandria 2,000 years ago. That spinning bronze sphere, dismissed as a mere novelty, was actually a glimpse into humanity's future, a future we're still living today. The Aeolipile teaches us patience with innovation, respect for ancient engineers who understood more than we often credit them with, and humility about how little we know about what future generations will find obvious. Sometimes the most profound inventions are the ones nobody recognizes as important until centuries have passed. And that sphere is still spinning, conceptually at least, in every power plant on Earth.